Hello everyone, and welcome to Chemistry is Everywhere. My name is Ton van Oefel, and today I will talk about sustainable ammonia production. Ammonia is the basic building block of nitrogen fertilizers. More than 200 million tons is produced annually. And why is nitrogen so important? When you look at the human body, nitrogen is the fourth most common element after carbon, hydrogen, and oxygen. It's in amino acids, in hemoglobin, it's in our DNA. And humans get nitrogen from plants or from animals that have been eating plants. Now, it's not that nitrogen is so rare on Earth. In the air, there is about 78%, but it's in an inactive form. The triple bond of the nitrogen molecule in air is one of the strongest bonds in nature. Most ammonia is produced by the Haber-Bosch process. Hydrogen is mixed with nitrogen at high temperature and pressure, and the energy consumption of this process is so tremendous that it is unsustainable in the long run. So research is focused on alternative routes to ammonia, and that's what we'll discuss today.
There are four main routes for reducing nitrogen to ammonia as alternatives for the Haber-Bosch process: biological nitrogen fixation, photocatalytic nitrogen fixation, electrochemical nitrogen reduction, and metal nitride looping. We will discuss each process in detail, including how it works, the challenges, and the development status. Biological nitrogen fixation is carried out by microorganisms that possess a nitrogenase enzyme complex. The enzyme's active site contains metal cofactors, typically iron molybdenum, that cleave the nitrogen triple bond and stepwise hydrogenate it to ammonia through a sequence of proton and electron transfers. This reaction is biologically energized by adenosine triphosphate, ATP, where the ATP cost reflects the energy investment by the cell to drive an otherwise very challenging reduction under ambient conditions. Biological nitrogen fixation occurs at ambient temperature and pressure in soil or symbiotic root nodules of legumes. The nitrogenase catalysis involves biological electron donors and tightly regulated cellular environments that also manage oxygen sensitivity. It is widely deployed in nature and already part of agricultural systems via symbiotic relationships, for example, legumes with rhizobium. Direct industrial use for ammonia synthesis is limited. The enzymatic process is not currently scalable to the millions of tons per year produced by the Haber-Bosch process because nitrogenase is oxygen sensitive, the overall ammonia production rate is low, and the requirement for cellular ATP limits throughput relative to industrial feedstocks. Research aims include engineering microorganisms or plants to fix nitrogen more efficiently or transfer nitrogenase activity to non-legume crops, but these are at experimental and field trial stages. Photocatalytic nitrogen fixation uses photocatalysts, typically semiconductors or engineered nanomaterials, to generate electron hole pairs. The photogenerated electrons reduce nitrogen, while holes oxidize water to supply protons and balance charge, ideally forming ammonia from nitrogen and water under ambient conditions via surface or adsorbed intermediates. Photocatalysis draws inspiration from nitrogenase to improve charge separation and surface activation, but fundamentally it remains a light-driven heterogeneous catalytic process. Studies include metal-organic frameworks, doped carbon nitride semiconductors, and single-atom catalysts designed to promote nitrogen adsorption, electron transfer, and reaction pathways. Photocatalytic nitrogen fixation is driven directly by photon absorption, unlinked to biological metabolism. Reductions occur on material surfaces under ambient pressure and temperature, often in water. Proton and electron transfer steps resemble simplified electrocatalytic mechanisms, but with the energy source being light rather than electrical potential. Photocatalytic nitrogen fixation is at the research and development stage, with demonstration of ammonia formation under light irradiation using specialized catalysts. Main challenge is the low solar to ammonia conversion efficiencies, often orders of magnitude below what would be needed for commercial viability. Advances include strategies to improve charge separation, defect engineering, doping, mimic biological active sites, and enhance light absorption, but commercial application is still far off. Electrochemical nitrogen reduction uses electrodes for supplying electrons and protons to nitrogen molecules at a catalyst surface. There are two pathways: associative, where the nitrogen molecule is hydrogenated stepwise via proton-coupled electron transfer, without full scission of the covalent bond, and dissociative, where the nitrogen bond cleaves first. The process operates at ambient temperature and pressure, but suffers from very low ammonia production rates and low Faradaic efficiency. Competition with the hydrogen evolution reaction is the main challenge. Research is aimed at nitrogen electrolyzers and catalysts. A few pilot projects are announced, but no commercial plant is in operation yet. Metal nitride looping is a process that decouples nitrogen activation and hydrogenation into separate steps using solid nitrogen carriers, such as metal nitrides. Instead of continuously reacting nitrogen and hydrogen over a single catalyst at high temperature and pressure, it uses materials that store nitrogen in their lattice and later release it as ammonia when reacted with hydrogen sources. This potentially enables ammonia production at milder conditions, with modular operation and compatibility with intermittent renewable energy. The core principle of metal nitride looping is to split ammonia synthesis into at least two reactions. Nitrogen fixation. A metal compound reacts with nitrogen gas at moderately high temperature to incorporate a nitrogen atom into its lattice. Hydrogenation. The nitrogen in the carrier's lattice is then hydrogenated, typically with hydrogen or another hydrogen source, to form ammonia. By separating these steps, the process can operate under lower pressures and temperatures for each partial reaction than the conventional Haber-Bosch route. Despite its attractiveness, metal nitride looping faces several technical and materials-level challenges. The nitrogen fixation step is often slow. Vacancies or defects may need to be engineered to enhance nitrogen incorporation. Carriers must withstand repeated cycles of nitridation and hydrogenation without sintering, phase segregation, or loss of capacity. Many early transition metal nitrides show promising ammonia evolution but degrade over cycles. Despite promising materials and high ammonia production rates in laboratory studies, industrial-scale deployment using metal nitrides has yet to be demonstrated.
Fritz Haber won the Nobel Prize in 1918 for the synthesis of ammonia from nitrogen and hydrogen, allowing the production of fertilizers and saving the world from hunger and starvation. After 100 plus years, his process has become unsustainable, and that's mainly because of the high energy requirements for the breaking of the nitrogen triple bond. We've been looking at alternative routes, and the main challenge here is high selectivity for ammonia. So in other words, minimal parasitic reactions such as hydrogen formation, and a high production rate, because we need those 200 plus million tons per year. Research groups worldwide are looking at new nitrogen carriers, new catalyst materials, and typically those are transition metals with unoccupied d orbitals. They can attract the lone electron pair of the nitrogen molecule. If you have a passion for chemistry, you want to fill Fritz Haber's shoes, let me know in the comments what you think will be the winning route. Is it metal nitride looping, or is it electronic nitrogen reduction? Let me know in the comments. A Nobel Prize might be waiting. Thank you for watching. Stay tuned, more episodes will follow.